Howdy, this is a presentation on Oxy Fuel Combustion. CO2 must be separated or captured from the flue gas before it can be geologically stored. There are three main methods for capturing the CO2 from fossil fuel combustion: post-combustion, pre-combustion, and oxy-fuel combustion. Oxy-fuel combustion is a fairly new approach to power generation. The process uses air that is stripped of other elements like argon and nitrogen until it's highly concentrated oxygen. It is then combined with a fuel, usually either coal or natural gas, into a stream of carbon dioxide inside a combustor. The fuel and O2 chemically react, and the resulting CO2 and H2O steam pushes a turbine that generates power. A major benefit of the oxygen-rich combustion is that it also results in pure CO2. In regard to the oxy-fuel combustion process, oxygen is separated from nitrogen in an air separation unit via cryogenic air separation, a separation method in which air is cooled down to the point where various gases turn to liquid. Because the temperature of liquid oxygen is negative 183 degrees Celsius and liquid nitrogen is negative 196 degrees Celsius, we can make oxygen liquid and separate it from nitrogen gas. Here we can see how the chemical equations differ for the combustion methods that we have previously discussed. We can see that the cost per megawatt hour of electricity for traditional power plants is much lower than for those with CCS technologies. We also notice that plant efficiency is lower for CCS technologies. This table shows a comparison between the advantages and disadvantages of oxy-fuel combustion capture, pre-combustion capture, and post-combustion capture. One of the main advantages of oxy-combustion capture is that it produces high-efficiency steam cycles. The Sankey diagrams were presented in May 2008 at the 7th Annual Conference on CCS on a poster titled Strategies for Improving Efficiencies in Oxy-Combustion Retrofits. The first diagram regarding air combustion shows how heat losses occur at the boiler and at the stack. Only a part of the energy flow at the power generator can be used, while a large chunk is thermodynamic loss. In the second diagram regarding oxy-combustion, heat from the boiler and compression is recovered and fed back. By using oxygen as the oxidizing agent, the combustion efficiency is more than doubled as compared with the conventional air combustion system because nitrogen, which is a substance which hinders the combustion as it absorbs the heat without heat transfer, is removed. Oxy-fuel combustion is a promising method of carbon capture and storage due to its higher boiler efficiency and high CO2 concentration in exhaust gases. All over the world, it is catching on. Here we can see one of the latest oxy-fuel pilot plants in China. As nitrogen, which accounts for 80% of conventional air combustion, is removed, the emissions after combustion is reduced by 80%. The CO2 emission is reduced as much as the fuel savings. Here are the flammability limits in oxy-fuel combustion compared with air-fuel combustion. In this set, 3 oxygen fractions are used. The results show that air-fuel combustion enjoys larger stability limits under all oxygen fractions considered. Carbon dioxide and sulfur dioxide emissions are a major concern in combustion processes using fossil fuels such as coal. The former is implicated in global climate change and the latter produces acid rain. CO2 is one of the major contributors to the buildup of greenhouse gases in the atmosphere. Today's state-of-the-art oxy-combustion systems would use a cryogenic process to supply oxygen, atmospheric pressure combustion for fuel conversion in a conventional supercritical pulverized coal boiler, substantial flue gas recycle, and conventional pollution control technologies. One technology that has been in development that could greatly assist in improving the efficiency of oxy-fuel combustion as well as integrated gasification combined cycle-based carbon capture is ion transport membrane technology. This technology is a membrane system for the capture of oxygen rather than carbon dioxide. This process, if successful, has the potential to replace traditional ASU systems in producing oxygen. Previously, we introduced three methods of carbon capture. Post-combustion capture is useful for separating CO2 from exhaust gases created by burning fossil fuels. Pre-combustion capture refers to removing CO2 from fossil fuels before combustion is completed. Oxy-fuel combustion is a fairly new approach to power generation. From these three pie charts, we can see the distribution of thermal power supplied to thermal power plants with coal gasification and CCS systems. It is noteworthy that oxy-combustion capture has significantly less cooling losses. The global carbon capture and storage market size was estimated at $3.28 billion in 2022 and is projected to grow at a compound annual growth rate of 7.1% from 2023 to 2030. Increasing carbon emissions across the world and surging concerns regarding the detrimental effect of carbon emissions on the environment have prompted the global adoption of carbon capture and storage technology.